We organized. I'll start working on my thesis. Graduation.
I'll probably give you a pink highlighter. You got a highlighter? All right, we need to get started here. We'll do quiz questions at the end. So let's finish off. Let's finish things off so we can do quiz questions at the end, because I want to talk about hybridization. So last time we filled in whether or not the molecules on this sheet would be nonpolar or polar. Now, and this is what the lab is. You can have a polar bond. If you have an electronegativity difference, and the lab does 0.5 or larger for a polar bond. The textbook, we did 0.39 earlier here. Polar covalent bond between 0.4 and 1.79. And then we know that the highest electronegativity has this bond dipole that's negative. We put a negative there, positive, for the one that is less electronegative. The more accurate way to do it is in our textbook, and that's called an Urquhart bond triangle. So that's on the next page, where on the next page, this triangle does electronegativity difference on the y-axis. It does the electronegativity difference on the y, and it does the average on the x. Difference, average. And then we end up more accurately by taking into account the average and not just the difference. We end up with ionic bonds in this region, covalent bonds in this region, metallic here, and this is semi-metallic. Now, the highest ionic bond is cesium fluoride. This has the greatest difference in electronegativity, correct? This is by far up here. Cesium is the lowest electronegativity. Fluorine is the highest. Here, to get something that's the most ionic, we have the greatest difference. The most covalent is in this bottom right corner. So the most covalent here in this bottom right corner that gets away from ionic, gets away from semi-metallic, this region over here, you have a small difference. And what else? What about the x-axis? You have a small difference on the y, and on the x-axis, you have a high average. Small difference, high average gets you covalent here. And if you have a metallic in the opposite left corner of this triangle here, your metallic bond here is going to be a small difference. Small difference on the y-axis. And what about on the x-axis? You have a small average. So high metallic bonds would be in this corner. Small difference, small average. If you have a small difference, you're talking about metals anyway, right? You're talking about metals. There's different electronegativity tables. So on the back side of our periodic table, again, cesium 0.79, francium, you can't do anything with francium, but cesium 0.79, fluoride 3.98, fluorine. But where's your high numbers? Right up in here with these nonmetals, right? So in order to get something covalent, you want something with a high average. Your average is about 4. You get something with a high average, you're way in this upper region. And you want a small difference. High, average, small difference. Now, if we use the electronegativities provided on the next page, I think I did an example for magnesium bromide. So we'll put it right here. MgBr2. So MgBr on the y-axis is my difference. So on my y-axis, I simply want to subtract these two. And let's see where they are on the next page. On the next page, MG's right here. And my bromine is down here. So I have 2.685. And my magnesium is 1.293. It doesn't matter. We're just going to get a difference here. 1.293 for magnesium, 2.685. We're going to do the absolute value of that. So our difference is 1.392. Right around 1.4. And on the x-axis, my average, I'm just going to add these two up and divide by 2. That's all you're going to do. So we have 1.293 plus 2.685 divided by 2. $1.99, really, 2. So now we have an ordered pair. To talk like a math teacher, we have an ordered pair. We have an X and a Y, correct? So 1.4 on the Y, right around 1.4 is going to get us about on this line, correct? $1.4 and about 2. We can see it's right there, correct? It's exactly where we would get an ordered pair for that. So we know for sure it's ionic. Now, if it's on this line, if it ends up pretty much on the line, like these right here, anything that's BeO, this would be about 50% ionic and about 50% covalent. And likewise over here, you'd have about 50% ionic and about 50% metallic. But that would make sense if it's right on the line. It's about 50-50. Okay, so that's how you do the bond triangle. There is a quiz question, there's a test question, there's a final exam question that just does this. Okay. On the test, I actually give you the triangle and I give you this table again. On the final exam, I gave you the triangle, I saved you the table, and I wrote in what the values are. But I think you can grid that out and do that. Okay, we need to talk to bring everything around now. We need to talk about this concept of hybridization. So if we go to our blue sheet, if we have 2 bonding domains, or if we have 1 bonding domain and 1 non-bonding domain, my electron pair geometry remains a 2, correct? My electron pair geometry remains a 2. This blue sheet is organized according to hybridization. I know it goes 2011, it goes 302112, but look at the hybridization matches the electron pair geometry. So my hybridization always matches this top number. Now, what I mean by that is this. Remember, we did 1s2, 2s2, 2p6, and we added up the electrons that were the superscripts up above? Well, this is an S1 and a P1. This adds up to 2, correct? Which is what this is. If you have sp2, how many do I have? I have 2 P's and 1 S, correct? What's my total for that? 3. All of these are 3. That's what this is. All of the hybridization here, 302112, is sp2. We're going to look at a videos on that. And we know that this would be linear. 20, yes. We know that this is trigonoplanar. This is trigonoplanar. If we go to 40, it's 1s, 3 p's. What's my total? 4, right? What does that look like? Tetrahedral. This is 40. This would be 3-1, but my electron pair geometry is still 4, right? If there's a non-bonded pair here. Then I can go down to this. This is water, right? What's my bonding domains for water? 2. How many non-bonding domains are there? 2. What's my electron pair geometry? Still tetrahedral, right? My electron pair geometry for everything here up is tetrahedral, correct? So sp3 again is 4. Then we go to 5. If your electron pair geometry is 5, it doesn't matter if it's 5, 0, 4, 1, 3, 2, 2, 3, 1, 4. My hybridization adds up to 1s, 3 p's, that's 4. And if you add a d, that's 5, right? My hybridization, we're going to look at the video. I just want to show you, though, is the same for all of these. What does that look like? It's trigonal here in the middle, the 120s, and then a pyramid on top and a pyramid on the bottom. So trigonal bipyramidal. Again, my electron pair geometry is the same for all of these. And then when I go to octahedral, this adds up. sp3d2, what does that add up to? 6. Okay, let me show you the videos. These are really good videos.
Let's first start by examining the shapes of the atomic orbitals for carbon. The 2s atomic orbital is a sphere, and the 3 2p atomic orbitals are shaped like dumbbells, oriented along the 3 axes, 2px, 2py, and 2pc.
Nothing new there, right? There's 3 different p orbitals. Well, they look like dumbbells, but they're orientated in space on the 3 axes. Nothing new. This is a spherical shape, right? For an S. Nothing new.
Think of these 4 atomic orbitals as 3-dimensional shapes, where you are most likely to find an electron 90% of the time. Notice that the electrons have access.
This is carbon. 1s2, 2s2, 2p2, correct? 1s2, 2s2, 2p2, and then according to Hund's rule, there's 1 electron here and 1 electron here. We did not pair them up. What are the valence electrons? How many valence electrons for carbon? 4, right? It's the 2s2 that you see here and the 2p2.
To both lobes for the 2p orbitals. Starting from the abbreviated electron configuration for
Again, 1s2, 2s2, 2p2, right?
carbon, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pz atomic orbital. Although we now have 4 unpaired electrons for bonding, we still can't explain the experimentally observed bond angles for a tetravalent carbon. Thus, when we mix the 2s atomic orbital with all 3 2p atomic orbitals, we create 4 new degenerate energy hybrid orbitals.
They're not s orbitals anymore. They're not p orbitals anymore. They're sp3 hybrid orbitals. I like the cartoon cat dog. It's cat on one end, dog on the other end. You don't have a cat, you don't have a dog, you got cat dog.
The shape of the new sp3 hybrid orbital is best characterized as 1 part s and 3 parts p. As with all orbitals, think of these hybrid orbitals as 3-dimensional shapes.
Again, they're not s's, they're not p's anymore. They're sp3 hybrids, or they look like a pacifier nookie.
Where you can find the electron 90% of the time. The hybridized carbon now possesses 4 unpaired valence electrons and is said to be an sp3 hybridized carbon.
So it doesn't matter if it's 4, 0, 3, 1, 2, 2, or 1, 3. What's your electron pair geometry? 4, correct? If it's a 4, 0, 3, 1, 2, 2, 1, 3, your electron pair geometry is still 4. These things want to get as far away from each other as they can.
When we superimpose all 4 sp3 hybrid orbitals onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. The 4 new hybrid orbitals attempt to get as far apart from each other as possible, 109.5 degrees. Think of this as the orbitals attempting to minimize repulsions between them. Thus, they are oriented towards the corners of a tetrahedron with all angles at 109.5 degrees. Your instructor will often draw the sp3 hybridized carbon on the blackboard as shown.
There's your 3D structure for lab. This is in the plane of the paper, straight up, down to the right. There's your 109 degrees, correct? This one is coming at me or towards you. This is behind the screen, right? So you do a wedge coming at you and a dashed line for behind. If your lab instructor wants you to do 3D.
The 2 solid lines in this drawing are in the plane of the board. The wedge represents the electron coming out of the plane of the board, and the dashed line represents the electron going back behind the plane of the board. Each of the 4 sp3 hybrid orbitals contains 1 electron capable of forming a covalent bond. The sp3 hybridized carbon is now capable of forming 4 covalent bonds. Here, X represents any atom with a valence electron capable of forming a covalent bond. Because the electron density is symmetrically located about an imaginary line that runs through the 2 adjacent nuclei, we call these bonds sigma bonds. An example of a simple carbon compound with an sp3 hybridized carbon is methane, CH4. The ideal bond angles are all 109.5 degrees, due to all 4 equal in size hydrogen atoms attempting to get as far away from each other as possible. Your instructor will often draw methane on the blackboard as shown.
This electron here, electron from carbon, hybridized electron. Think of them as spinning all the same direction, and the hydrogen electron spinning opposite. So when they bond up here, you've got opposite spinning electrons.
Again, the two solid lines in this drawing are in the plane of the board. The wedge represents one of the hydrogens coming out of the plane of the board, and the dashed line represents one of the hydrogens going back behind the plane of the board. Another simple carbon compound that utilizes sp3 carbons is ethane. From the two-dimensional Lewis diagram, we see that each carbon has 4 single bonds. Thus, both carbons are sp3 hybridized. Starting with 2 sp3 hybridized building blocks, we can start to construct the molecule in 3 dimensions by forming the CC sigma bond.
Sigma bond right there.
Next, the 6 hydrogen sigma bonds are formed, which affords the final 3-dimensional structure for ethane. The 2-dimensional Lewis diagram for ethane implies that all 4 bond angles are 90 degrees. However, employing the basic principles of hybridization theory, we see that the bond angles are all nearly 109.5 degrees. Now that the molecular geometry for ethane in 3 dimensions has been determined, we can begin to examine some of ethane's interesting physical properties. For example, free rotation may occur about the carbon-carbon single bond, which allows us to explore simple conformational analysis. Conformations are different arrangements of.
I remember coming home from school and pounding on the door, but my mother wouldn't answer.
Similar to the first step of sp3 hybridization, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pz atomic orbital. Mixing the 2s atomic orbital with 2 of the 2p atomic orbitals creates 3 new degenerate energy hybrid orbitals.
Now look at how many orbitals came together? 3. 1s, 2 of the p's. What does that leave us? A regular dumbbell-shaped p. Right? That leaves us a regular dumbbell-shaped p. These are 3 hybrids. If I have S1, P2, that's 3, correct? I have 3 hybrid orbitals.
The shape of the new sp2 hybrid orbital is best characterized as 1 part s and 2 parts p. As with all orbitals, think of these hybrid orbitals as 3-dimensional shapes where you can find the electron 90% of the time.
Regular p
The
left
sp2
over.
hybridized carbon now possesses 3 electrons in hybrid orbitals and 1 electron in a non-hybridized 2pz orbital. When we superimpose all 3 sp2 hybrid orbitals with the unhybridized 2pz orbital onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. In addition, the electron density of the unhybridized p orbital is shrunk to 1/3 of its size for simpler viewing. The 3 new hybrid orbitals attempt to get as far apart from each other as possible. Again, think of this as the hybrid orbitals attempting to minimize electron repulsion. Thus, they are oriented 120 degrees apart. Your instructor will often draw the sp2 hybridized carbon on the blackboard as shown. Again, remember that solid lines are in the plane of the board, wedges are coming out of the plane of the board, and dashed lines are going back behind the plane of the board. Before we begin to show how the sp2 hybrid building block takes part in bonding, it is important to remember that the electron in the unhybridized 2p orbital has access to both lobes. Each of the 3 sp2 hybrid orbitals contains 1 electron capable of forming a sigma bond. Thus, the sp2 hybridized carbon is now capable of forming 3 sigma bonds and 1 pi bond. A simple carbon compound that utilizes sp2 carbons is ethylene. From the two-dimensional Lewis diagram, we see that each carbon forms 3 sigma bonds and 1 pi bond. Thus, both carbons are sp2 hybridized. Starting with 2 sp2 hybridized building blocks, we can begin to construct the molecule in 3 dimensions by forming the CC sigma bond.
Those is from 2 hybrid orbitals coming together, correct? That sigma bond there is an electron in a hybrid orbital here and an electron in a hybrid orbital here, sigma bond.
Next, the 4 carbon hydrogen sigma bonds are formed, which affords the planar sigma bond framework for ethylene. To form the second bond between the carbons, called the pi bond, we can imagine that the 2 adjacent parallel unhybridized 2pz atomic orbitals overlap. When they overlap, the 2 electrons can be shared, allowing each carbon to attain full valency.
Whoa, whoa, whoa. How do you get a double bond? If you have a double bond, one of them is going to be sigma, one of them is going to be pi. How do you get a pi bond? Unhybridized parallel p orbitals, right? Those orbitals here started out what we would call in the y plane, correct? It's a y plane from the right carbon. It's a y plane from the left carbon. They overlap. If you have a double bond, one of them is sigma, one of them is pi. How do we get the sigma bond? 2 hybridized orbitals, 1 electron in each came together. How do we get a pi bond? Unhybridized parallel p orbitals.
The two-dimensional Lewis diagram for ethylene allows the chemist to view the gross connectivity of the atoms. However, no information is to gain a better understanding of the pi bond. We should recall the actual shape of the unhybridized p orbitals. When we envision the actual shape of these orbitals, overlap between the adjacent p orbitals is possible, which allows for the sharing of these 2 electrons. However, it is very difficult to draw the molecule this way. Thus, you will often see the pi bond represented in its abbreviated form on the right.
When we first arrived at St. Jude, it was just Claire and I. She was still recovering from When we first arrived at St. Jude,
Similar to the first step of sp3 and sp2 hybridization, one can imagine promoting an electron from the 2s atomic orbital to the unoccupied 2pz atomic orbital. Mixing the 2s atomic orbital.
We have an S gets together with a P, correct? That leaves 2 unhybridized p orbitals, yes? We have 2 unhybridized p orbitals left. Which ones morph together? You don't have an S, you don't have a P anymore. You have sp hybrids.
With one of the 2p atomic orbitals causes 2 new degenerate energy hybrid orbitals. The shape of the new sp hybrid orbital is best characterized as 1 part s and 1 part p. As with all orbitals, think of these hybrid orbitals as 3-dimensional shapes, where you can find the electron 90% of the time. The sp hybridized carbon now possesses 2 electrons in hybrid.
We could do sigma bonds here, yes? And we could do pi bonds here. Notice there's 2 of them. One on the y-axis, one on the z-axis. Unhybridized p orbitals.
And 2 electrons in the unhybridized 2p orbitals. When we superimpose both sp hybrid orbitals with the unhybridized 2pz and 2py orbitals onto the carbon atom, it becomes quite cumbersome and confusing. Thus, we simply show how the electrons in the hybrid orbitals are oriented in 3 dimensions. In addition, the electron density in the unhybridized p orbitals is shrunk to 1/3 of their size for simpler viewing. The two new hybrid orbitals attempt to get as far apart from each other as possible. Again, think of this as the orbitals attempting to minimize electron repulsions. Thus, they are oriented 180 degrees apart. Before we begin to show how the sp hybrid building block takes part in bonding, it is important to remember that the electrons in the unhybridized 2p orbitals have access to both lobes. Your instructor will often draw the sp hybridized carbon on the blackboard as shown. Again, solid lines are in the plane of the board, shaded lobes are coming out of the plane of the board, and dashed lines are going behind the plane of the board. Each of the two sp hybrid orbitals contains one electron capable of forming a sigma bond. The sp hybridized carbon is now capable of forming two sigma bonds and two pi bonds. A simple carbon compound that utilizes sp carbons is ethyne, or acetylene. From the two-dimensional Lewis diagram, we see that each carbon forms two sigma bonds and two pi bonds. Thus, both carbons are sp hybridized. Starting with two sp hybridized building blocks, we can begin to construct the molecule in 3 dimensions by forming the cc sigma bond. Next, the two carbon-hydrogen sigma bonds are formed, which affords the linear sigma bond framework for ethyne. To form the second and third bonds between the carbons, called the pi bonds, we can imagine that the two pairs of adjacent parallel unhybridized 2p atomic orbitals overlap. When they overlap, the 4 electrons can be shared, allowing bonds between the carbons called the pi bonds. We can imagine that the two pairs of adjacent parallel unhybridized 2p atomic orbitals.
Two of them parallel unhybridized p orbitals.
Overlap. When they overlap, the 4 electrons can be shared, allowing each carbon to attain full valency.
If you have a triple bond, you have 1 sigma and 2 pi, correct? 1 sigma, 2 pi. The blue is in the Z plane, or I guess X plane here, the way they did it. I guess it would be Z plane, and the reds are in the Y plane. Triple bond, 1 sigma in the middle. Where do you get the sigma bond? Hybrid orbital from each, correct? A hybrid orbital from each, and then you have 2 pi bonds.
The two-dimensional Lewis diagram for ethyne allows the chemist to view the gross connectivity of the atoms. However, no information is conveyed about the pi bonds. When a molecule is represented in 3 dimensions, we see that half of each pi bond is above and below a p.
Because on any given
And
day,
understand
we're all mechanics, carpenters, fixers, DIYers, and training wheel taker offers. We also know no one should overpay for dependent. Any given day, we're all mechanics.
while the pi bond seeks carbon
I'm going to skip ahead
for
here.
each atom.
This is what I want to show
Employ
you.
the sp hybridized building block. And 3 groups employ the sp2 hybridized building block for both oxygen atoms.
Notice carbon has a pi bond on the right, a pi bond on the left, right? So we're looking at a sigma and a pi and a sigma and a pi. And oxygen is hybridized as well. sp2 hybridized.
Starting with one sp and sp2 hybridized building blocks, we can start to construct the molecule in 3 dimensions by forming both CO sigma bonds. For both pi bonds to form, we need to rotate the oxygen on the right forward so that the adjacent unhybridized 2p orbitals are parallel. Thus, both pi bonds form, forming the final three-dimensional molecule. Notice that the two pi bonds are perpendicular to each other. In addition, the lone pairs on each oxygen atom are perpendicular to each other. As you become comfortable with the concepts of hybridization, you will be able to fold two-dimensional Lewis structures into three dimensions in your mind. With practice, you will also be able to allow the molecule.
All right, let's go to our quiz questions right now. Click out of this. What happened here? Did I click out of this? Well, it seems like I can just skip this recording. Nope. Here we go. All right, let's do our quiz questions. Okay. 25. What is the hybridization of the central atom? Now, I wrote the test so that you do not need the blue sheet. So if we're doing I3 minus, how many valence electrons do I have for this? And I'm going to go like this, right? I'm just going to go 3 I's. Iodine is in group 17, so we're going to have 3 times 7 plus 1, right, for the negative charge. So it looks like we're going to have 22 electrons. Agreed? 22 electrons? 22 electrons. First thing we need to do is this. Now we need to complete the octets on the terminal atoms. We can't do any double bonds with this. So that's 16 electrons, correct? So that's 16, 17, 18, 19, 20, 21, 22. And technically this would have, it would look like this. What's my electron pair geometry on the central atom? How many total bonds would I have on the central atom? How many total bonds can I have on the central atom? 5, correct? 3 non-bonded pairs plus it's bonded to 2. It's 5, right? So now you just start adding up. I need a hybridization of 5. There's sp3, that's 4. And believe it or not, you can have a D as well. That should be my hybridization right there, because this totals up to 5 orbitals coming together. So again, you could have sp3d get together. There's not S's anymore. They're not P's anymore. They're not D's anymore. They're sp3d hybrids. So we know the answer to this is this. If we looked it up on our blue sheet, we would look this up as a 2,3, right? And if we looked up a 2,3, look at what we get. 2,3, we get sp3d. So all we need to do is count how many hybrid orbitals. That has to match your electron pair geometry. So I modified the test so you can just do the question like this. You don't need the blue sheet. We're not using the blue sheet for the test. You can use the blue sheet for the final though. Okay. So let's do the next one. Same thing. What's the hybridization if we have NCl3? Well, my valence electrons here for nitrogen is 5, right? 5 for the nitrogen. This is in group 17. So it looks like we have 26 valence electrons. 26 valence electrons, nothing new there. So if we go N, Cl, 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 and if we connect them and then complete our terminal octets, that gives us 24, correct? 24 right there. I just have to put a non-bonded pair there, correct? My electron pair geometry is 4, yes? How do I add up 4 hybrids? You know, we start with the SP3 gives me 4 total across there, correct? I know this is SP3. If you looked on your blue sheet, you would do a 3-1, you'd get SP3 anyway, but we know that's SP3. Oops, did I just circle the wrong one? SP3 here. I circled the wrong one. Big D on that one, right? SP3. Okay, 27. Which of the following compounds would be nonpolar? If it's nonpolar, everything has to cancel out, correct? Typically, the terminal atoms have to be the same. There are some flukish things where you could have these 3 atoms at 120 could be the same, and the top and bottom could be the same, different atoms. That would be kind of a fluke, and that would be still nonpolar, right? But that would be kind of a fluke. So we've got carbon here. All of these are bonded like this. So remember, that is not 90 degrees. This is 40. This is tetrahedral, correct? The only one that could be nonpolar would have to be this one. Right? Because I cannot get, you might say, oh, well, D can be nonpolar. So I'm prepared for that. So here's my CCl2. Or no matter what. Here's, let's call these CLs, and those are Fs. No matter what, if something is sp3 hybridized, I cannot stick these straight across from each other. It doesn't matter what place I put this now. It's going to end up being the same. No matter what, those are not going to go straight across from each other. What's the molecular formula of this compound? Add up the carbons and the hydrogens and the oxygen. 28. Did I miss 17? Let's backtrack to 17. Okay. You have to draw these out. You have to draw the Lewis structure for all of these. And then you're just looking to see if the central atom has less than 8 electrons or more than 8 electrons on the central atom. Does the central atom have less than 8 or more than 8? But you actually have to draw the Lewis structure for those to find out. Let's do number 30. How many sigma and pi bonds are in the following molecule? If you have a double bond, what do you have? You have one sigma from a hybridized orbital and one pi from an unhybridized parallel p, correct? And if you have a triple bond, what do you got? What's that made a triple bond made out of? Two pi's and a sigma, correct? Or you could end up with carbon with a double bond on each side, like carbon dioxide. So when we look at this sigma, 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 sigma for all your single bonds, sigma. And when you have a double bond, one of them is a sigma, and one of them is a pi bond, right? If you have a triple bond, you're going to have one sigma, and you're going to have two pi's no matter what. One sigma, two pi's. Let's do 29. Which of the following statements is correct? The overlap between an s orbital and the p orbital is a pi bond. How do you get a pi bond? Both of them have to be parallel p's, right? Unhybridized parallel p's. This is junk. The overlap of two 1s orbitals in HS is called a sigma bond. So let's go up here and look at number 2. I should draw this a little better. Let me try this. This is hydrogen bonded to a hydrogen. That's just hydrogen gas, H2. What is this? This is 1s1. This is 1s1, huh? So you can picture that as one electron in one spinning one direction, one electron in the other spinning the other direction to make the bond. And that is a sigma bond. That would be fine. Just an electron from each, right? HF is formed from the overlap of hydrogen 1s. We looked at a hydrogen 1s. We're good with that. With fluorine 2s. What's the fluorine's electron configuration notation? One S2, 2s2, 2p5. Where's that single electron going to be in fluorine? It's going to be in a p, right? You're not going to go back into the 2s. It's going to be from a 2p. So this is junk. This would have to be a 2p. Okay. What I'd like to do now is help you finish up some OWL. I actually have them here. This goes through sigma and pi bonds. And this is actually the quiz question we just looked at on page 14. But let's look at some OWL examples I have here. So this actually is the question that we just looked at. Hybridization. This just shows the overlap again for hybridization. This looks at your shapes. Al does actually a pretty good job with that. So I think we should be, I must have the wrong one out here. Page 22. Now, I don't know if you finished up Owl. Some of you are finished. Well, maybe I should have actually put this on the screen. But this does work out pretty well. You can spin this in Owl. So I took a screenshot from Owl. It says rotate the molecule until you have a feeling for its three-dimensional shape. How many atoms are bonded to the central atom? Well, in this case, I've got 3 bonded to the central atom. If you consider only the 3 outer atoms, what shape do they define? Well, a triangle. What is the approximate numerical value of this angle? Well, it's 109.5 if they were all the same. And if I take one of these out, it actually goes down, but approximately 109. Does the central atom lie in the plane defined by the 3 other atoms? What we're saying is this. Can you draw a line through the center of all 4 of these at once? No, they're not in the same plane, correct? These 3, you should be able to draw a line through these 3. These 3 here are in the same plane, but not this one. You can't draw a line through all 4. So the answer to that is no. Are all 3 positions about the central atom equivalent, or is one of them different from the other 2? So all 3 of these are positioned the same. They're all the same. For practice, type in the name of the geometry of the molecule, trigonopyramidal. So on the next page, this has 5 on the central atom. So rotate the molecule until you have a feeling of the 3-dimensional shape. How many chlorine atoms are bonded to the central atom? 5 in this case. A molecule with square pyramidal geometry would result if one of the outer atoms were removed from an octahedral molecule. Does it matter which of the outer atoms is removed? It does not. Are all of the outer atoms geometrically equivalent or in a square pyramidal molecule, or are there 2 types? Well, there's 2 types. In this case, you have 4 of them in one plane and 1 of them in the opposite plane, correct? There's 2 types. What is the approximate angle? 90 and 180 is opposite from it, be 180. For practice, type in the name of the geometry, square pyramidal. When you rotate, you're going to see these pretty good. And then look at your blue sheet as well. So here's a bonding question, what we just went through. Hybrid orbitals and sigma bonds. A pi bond arises from the straight on a sigma bond, not a sigma bond, arises from the straight-on overlap of two atomic orbitals. The electron density lies along the axis of the bonded nuclei. Sigma bond. This is the bonding in methane, CH4. Think of this as one electron from hydrogen and then one hybridized, spinning the opposite way. That's not showing up very well. Here we have CH2O, carbon to a hydrogen and a hydrogen. You know, carbon needs 4 bonds. Oxygen needs 2 bonds, either 2 singles or a double, right? So in this case, we'd be looking at double bond here. This is sigma, 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 pi. What is the hybridization going to be? This is a 3-0, right? Remember, this pi bond is not done with a hybrid orbital. This is a regular p orbital left over. So this is going to be sp2. That's a 3-0. sp2, 3 hybrids. Then pi bonding here, we know pi bond is overlapping parallel p's. So I'll talk propine here. And hopefully you remember how to draw these out. We did it towards the end of our Lewis structure. In fact, this is the very last thing. But we did it early. You want to connect the carbons? So we had carbon 1, carbon 2, carbon 3, hydrogen, 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 1 hydrogen here. How do we fix this up? We need to make a triple bond here, correct? Now, all you have to do is add up your sigma bonds to get the hybridization. This carbon here has how many? Actually, just asking how many bonds. This is a good question. Okay. So this is carbon 1. Carbon 1, carbon 2, carbon 3. How many sigma bonds here for carbon 1? 1 on the left, 1 on the right, correct? So it has 2 sigma bonds. How many pi bonds does carbon 1 have? 2, right? Because carbon 1 is making a triple bond. In a triple bond, 1 of them is sigma, 2 of them are pi. Okay. Go to our quiz. Um. $23. Based on the given bond type triangle, what is the highest possible average to keep some metallic character? Highest possible average to keep some metallic character. So we're in this region, correct? Where's my highest average going to be? Going along the right on this x-axis, correct? Look at my numbers. It looks like my highest average I can get would be somewhere like right in here, huh? Right about here. My highest average, if I go down 1.8, 1.9 if I push it. Highest average to retain metallic character, 1.8, 1.9. Yeah, it looks like we've got 1.9. Let's do 24. Which of the following molecules is polar? Okay. If we did A, I think we've done this enough that we know we've got this for carbon dioxide, I'm hoping. And for the carbon dioxide, which one's more electronegative? Oxygen, correct. But oxygen's pulling to the one, oxygen's pulling to the right, one's pulling to the left. That's going to cancel out. This is nonpolar, yes? This is going to cancel out. We know this is nonpolar. If we do B, we've got SO2. How many valence electrons do we have there? We've got 18 valence electrons. Okay. Am I missing? Let's see, SO2. If we didn't put a double bond into this, 16 valence electrons? No, what did I do here? 6 times 3. I need 18. I've got 16. Okay. I wonder if that's going to be, why am I, if we could put 2 here, but that's not going to do it, is it? We have to do, make multiple bonds here, huh? So we would have resonance structures here. So if we did it this way, we're going to have one or the other. Okay, this leaves us with a non-bonded pair, so this should be polar. Leaves us with a non-bonded pair here. That should make that polar. In C, we have SF6. SF6, wow. So for SF6, we've got 6, 42, 48. Wow. But 6 times 8 is 48, right? Shouldn't even keep going, but. What about this? Can you visualize that? We've got this, right? We've got. Or in this axis. 90, 90, 90, correct? And then top and bottom. So we have this. I need to bring my meter sticks. Everything's 90. Everything's going to cancel out. That's nonpolar. So we know that this is nonpolar. And the question is, what about ozone? Now, ozone we've done before. It ends up being bent. But let's do that. So oxygen is going to be 6. We need 18 electrons. So there's 16, 17, 18. And it's going to look like B. We're still going to have to do resonance, but we're going to have a non-bonded pair. So it looks like both of those would be polar. Okay. Boy, that really narrows down this quiz. Based on the bond triangle, I think you could do that. So for the test Thursday, there's a list out there in Canvas, correct? I would look at your take-home quizzes to match up that description, but that is in Canvas, correct? Now it's 30 questions. It's 30 questions, and it is not as difficult of a test. It's not a horribly difficult test. Then for your final exam, which is at 8 a.m. Tuesday, there is a recording out there and a list in Canvas. Just scroll down. Correct? There's a recording and a list. I go through the list on the recording. So we're going to do this, the same test thing. You'll get a Scantron. Everything will be on there. So questions? All right. We'll see you Thursday.
It's the final of this.